Give me one more moment here. I'll need to turn this sound down on that. And then Mehmet, I'll give you the cue to start. It'll be just another minute or so here, hopefully less. Give me one more moment here. All right, Mehmet, you can go ahead.
Okay, good evening. This evening, our speaker is John Groubert. John is a lifelong amateur astronomer, having started in the hobby when he was a teenager. He came to Denver in 2016, about the same year that I was, but he joined DAS, Denver Astronomical Society, as he was unpacking his boxes the very first night. In my case, it took me 3 months before I decided to join. John works at the local telescope store, Mile High Astronomy in Lakewood. He owns 4 telescopes, but he claims he has his addiction under control, if you believe him. He's also a former attorney, New York attorney. So let him know if he is speaking too fast. I guess his current job must be more fun than his previous one. So John, the floor is yours for the presentation. John, can you hear us?
There we go. Sorry about that. Okay, I'm back. Yes, I'm not exactly a technical person, especially with Zoom. Thank you, Mehmet. Thank you, Dina. Thank you, everybody else, for being patient through all these technical problems, but we could get this started now. Yes, as Mehmet said, I have been a lifelong astronomer, and this is a passion for me, and it's definitely a lot more fun being a clerk in a telescope store than it ever was being a lawyer. So this presentation is about for newbies, for beginners, for people who just don't know what they're doing. They have the telescope, and now what's next? So one of the first things that you want to do is you definitely want to read your manual. I know that's not what you want to hear from a presentation like this, but there actually are a lot of questions that are answered just by the manual, and you do want to take a look at that. There's a lot of information in there. Another thing you can do is if you go to YouTube and you type your scope in, your model of scope into YouTube, you're going to find a dozen videos from people that are going to explain a whole bunch of things. So that's going to be helpful as well. But let's assume that you haven't done either of those things. One of the first things that you do when you take your telescope out is you want to level it. Now, this is more important for telescopes that are computerized and motorized. So if you have, say, a Dobsonian or just a manual refractor, leveling isn't as important. I mean, you want to have a nice level scope. But if your telescope is computerized and motorized, in that case, you're really doing yourself a favor by keeping your scope really level. It's going to help the computer and the motors on your scope be able to locate objects for you a lot easier. What you're looking at here is this is just a simple bubble level. Right here on the right, you see that the bubble is in this red, it's outside of this red level here. And you want to lengthen and shorten the legs until you get that as level as you possibly can. It might take you a couple of minutes. It's definitely worth it, and it definitely increases the accuracy that you're going to have. Another thing, of course, that you need to do is you need to focus your telescope. So here on this refractor right here is the focus knob. If you haven't seen that, here on a Dobsonian is the focus knob right here. And here on your Schmidt-Cassegrains or Maxitovs, the compound telescopes, is your focus knob here. And what you are looking to do is, if you are having trouble, if everything is blurry, and working in the store, we hear this quite a lot, that things are just really blurry, take the telescope out during the day and focus on something that's not your neighbors across the street or down the block, something that's a good half a mile away, a mile, mountains, anything that's really far away, and just keep on turning those knobs until you can see it. When you focus during the day, it's a lot easier. You're going to see it go from a blurry image to a clearer image. And I can't tell you which way to turn the knob, whether it's clockwise or counterclockwise. You're just going to turn the knob its full range until you can until the image starts getting clearer and clearer. So that's the general idea with focusing. If you do that during the day, you take the telescope out at night, you're going to be able to have a pretty close focus to what you need to be. Unfortunately, what some people do is they take the telescope so far out of focus that they just think, oh, well, I can't see anything. There's something wrong with the scope, and they don't focus it back to where they initially started off with. So take it out during the day and try that. Computerized telescopes have handsets. And so this is a representative of, on the left is the Celestron type of handset, on the right is the Meade type of handset. You're going to notice on the Celestron one that all the buttons are labeled, and that's really, really helpful. The Meade just has, the numbers here, and everything's going to be on the screen, and the screen is only 2 lines, and it's only about 16 letters per line, so it's very limited. So on a Meade, it's a little bit harder to figure out what your next step might be. On the Celestron, the buttons are labeled, and that's going to be able to help you figure out what you need to do. And so going through how to actually work this is beyond the scope of this talk. You definitely want to look at your manual for that. You definitely ask me questions about it if you're having trouble at the end of the presentation. But you can also, that's also where the videos are very strong. If you go to YouTube and watch the videos, they're going to explain how everything works. What I will explain right now is the red dot finder alignment. This is really important. It's critical, not just for manually operated telescopes, meaning your Dobsonians or your regular refractors that you're just moving around. It's also critical for your computerized and motorized telescopes as well. And the reason why this is important is you want to use your red dot finder to get your telescope on target. If your red dot finder or a finder scope, but the concept is very similar, if the red dot finder or the finder scope are off target, you are just going to have that much harder of a time getting everything into the main view of the main telescope through an eyepiece. So you really want to take some time to do this. What you have to do is you got to take the telescope out during the day, and you will, again, not on the house across the street, not on something down the block. You want to point the telescope at something that is very far away as you can get it. Quarter mile is all right, a half mile is better, a mile is even better. If you want to do it on the mountains, that's great. I usually try to pick out something like a church steeple or a radio tower. Something that's really far away that you can avoid the parallax between your telescope and the red dot finder. I'm obviously exaggerating that they're pointing in different directions. You want them as parallel as possible. And what you do with the red dot finder or the finder scope is you point it at something far away, you center the object, you put the red dot over that object. So it's not just over the church steeple, it's the cross of the church steeple. It's not just the radio tower, it's the blinking red light of the radio tower. And then you, whatever it is, it has to be something very definitive and distinct from anything else that's around it. So you aren't just lining up on one mountain peak and then through the telescope, you're lining up on the mountain peak, one peak over. When you do that, then you go to the main telescope and you look through the eyepiece. If you look through the eyepiece, and you see that church steeple is centered in the eyepiece, you see that blinking red light is centered in the eyepiece of the main telescope, great, you're done. But it won't be. Even though it looks like the red dot finder or the finder scope are pointing in exactly the same direction, it will be off by a degree or half a degree. And if it's off by half a degree or a degree, it's going to affect your ability to use your telescope later on at night. What you do is you move the telescope ever so slightly. You might have slow motion controls. You might be able to use the handset to move the telescope in a slow fashion so that whatever it is now lined up in the main telescope. Well, okay, great. Now the finder is off. you have three things on the finder. This is the on the red dot finder, you have an on-off switch here. And this is also what's called the rheostat. You can turn this so you can increase the brightness of the red dot as much as possible. And when you're doing this during the day, you're going to turn this knob as far as it goes. You'll hear a click when you first turn it on, and you'll turn it all the way. Then you're going to use this knob here and this knob here to change the alignment of that red dot finder. This one here is going to move the red dot finder left and right. This one is going to move the red dot finder up and down. And you're going to go back and forth between the dot on the red dot finder. You shouldn't be moving the telescope at this point, but if you accidentally do, go back and forth, back and forth, back and forth between the eyepiece of the main telescope and where that red dot is placed until you get both centered on exactly the same target. The reason why you're doing this during the day as opposed to at night is, first of all, you don't want to take away from your observing time, and it's cold outside. It's a little bit warmer during the day. But the real reason is that if you're doing it with something on the Earth, then whatever it is you're doing it on is not moving. You can do a red dot finder at night, but you would probably choose a star. And if you choose a star, well, that star is going to move with the rotation of the Earth. And it's just going to make it a little bit harder for you to get that alignment accurate. And it's going to take longer for you to do that. So it's easier to do this during the day and get the telescope set up that way. Next thing you need to do, we're going to move away from the computerized and motorized telescopes towards the manual telescopes. These are your Dobsonians. These are your refractors, your general refractors that cost anywhere between $200 and $400. These are star maps. These are star atlases here. Right here we have, this is, if you might recognize this as Orion's belt. And so you've got Orion's belt here. Don't mind my dog. He's just going to bark for a minute while my wife comes in from skiing. You've got Orion's belt here. Here's the Orion Nebula down here. Over here, you've got the part of the constellation of Scorpius. You can see the tail wrapping around, and there's a lot of objects to look at here. What you can do is you would point your telescope here, for example, this is the star Antares. You'd point your telescope here, and then you just move it over slightly, and you'd see what's called a globular cluster. And this is a globular cluster. It's called M4 right here. Here, the Orion Nebula is actually really easy. Let's try up here. We have M78. So here's a blow up of that view. And what you do here is you'd start off, you have the three bright stars of the belt, really easy to identify, really easy to see. You would start with your viewfinder or your red dot finder, and you'd move up to this star here. And then you'd move up again, a little further, twice the distance to that star there. And then you'd move over, whoops, sorry about that. You move over to the left. That distance there was about the same as this distance here. It's pretty much an equilateral triangle. And you would put the telescope right on this area. Okay, and then you'd have M78 in the view of your main scope. And so that's actually a rather difficult object to find and to look at. But I'm just giving you an example of how you would do the star hopping. If you have a finder scope, and that's a little telescope that's not a red dot finder, if you have a finder scope, it would actually be easier to do the star hopping. So with a Dobsonian telescope, you'd have a finder scope, you'd start again on the left belt star of Orion here. You'd move up a little bit to this bright star here. Then you'd move up again and be able to see these stars in between right here and here. And that would guide you on the way towards finding M78. In fact, if you had a finder scope, when you started out on the belt of Orion, you can see here there are markings on the side that show how many degrees in the sky this is. And the degrees in the sky are easy to explain. If you have the from horizon to horizon, I can't get my hand straight like that. If you have from horizon to horizon, that's 180 degrees. If you have from the horizon to the zenith, to the top of the sky, that's 90 degrees, just like a 90-degree angle in a triangle or something, or in a square. And so these markings here show 2-degree increments on the sky. A finder scope will generally have at least a 5-degree, if not a 6-degree field of view. So you're going to be able to see all of this. It's less than 4 degrees from one side of the belt to the other, and it's less than 4 degrees. It's about 2, maybe 2.5 degrees from this side of the belt to M78. And so it's going to be easier to find something like this if you're using a finder scope, but you can also find it with a red dot finder if you're just a little bit clever in terms of how you're moving the telescope. Your telescope will also have what's called a field of view, which I'll talk about a little later, and you might be able to see from this star is called Alnitak all the way to M78 in the same view at the same time. However, many telescopes don't have a 2 to 2.5 degree field of view, so you would just move the telescope towards these stars and then over, and then look and see if you can see M78. Again, M78 is not really the best example, but I just used it because Orion is such a familiar constellation. M78 is actually a pretty tough get. So maybe don't start off with M78. The best book for this type of star hopping is Turn Left at Orion, period, end of sentence. This is absolutely great book. If you're starting out and you're trying to find things, this is what the book looks like. It's a 2-page spread for most of the objects in the sky. So here's a globular cluster in Hercules called M92, which is a really lovely globular cluster, and we'll see what a globular cluster is a little bit later on. But it's just a random object, a random page. What Turn Left at Orion does for you is it shows you, okay, here's the constellation. This is where you're going to be looking at in the sky. And it's showing you where you're going to point your finder scope. So this is geared for a finder scope. And this is a 6-degree field of view. So this view here and this view here are the same. And so this is what the view would look like through your finder scope. And it has that picture, and that's the next step. And you're going to put you're going to look around. These are other stars that are outside of that field of view. And then when you go and you put that where it's supposed to be in the sky, then you look over here and it shows you this is the view through the telescope itself. What's important to notice here, these aren't photographs, and these aren't reversals of photographs either, negatives of photographs. These are what I would call computerized drawings. And so what I mean by that is that they have taken the view of M92 and sort of drawn it out on a computer to give you what it would look like this is in a small telescope, if you can't read that, and this is in a Dobsonian telescope. A small telescope, it's usually about a 4-inch telescope under dark skies. In a Dobsonian telescope, it's usually about an 8-inch telescope under dark skies. And this book is just outstanding that way in helping you do that star hopping. The next thing about the book is that for each of these objects, you're getting a description of the object. So here it's describing what M92 is, and I can barely read it on my screen. I'll give it a shot. It says M92 is a collection of at least several 100,000 stars in a ball roughly 100 light years in diameter. And it goes on. And so it's important to know that when you are looking up at these objects, some of them are impressive and really cool, and some of them are just not impressive. And you look at it and you go, huh, well, that's it? That's all I got here? And so if you know about what the object is, you will really, really enjoy it more. You'll really get a lot more out of it if you understand what you're looking at. If you understand that what you're looking at is a ball of stars that's 35,000 light years away, that becomes more impressive. Now, M92 actually is a really nice object to look at. And it's a spring object, so you'll be able to see it in about 3 or 4 months. If you don't have if you're not using a manual scope, if you're using a go-to scope, this book really won't do too much for you. A lot of what this book is geared towards is helping you find the object. And it does have the explanations, which are nice. But you can look up the explanations yourself on, say, Wikipedia or somewhere and find out what the explanation of the object is in a different source, and you could do that for free. But on the other hand, if you are using a manual scope, this is the book for you. So let's talk about magnification. Your telescope came with at least 1 eyepiece, maybe 2, maybe 3. And so what you need to understand is the formula for figuring out what magnification is. And it's really simple. And near your focuser, that's where the eyepiece goes, near your focuser, you'll probably see a sticker. And if you don't have a sticker on your focus, near where your focuser is, where your eyepiece is, look at the front of the telescope. The front of the telescope has some information on this outside ring. And so, for example, for this telescope, this is an 8-inch Dobsonian. It has a diameter, that's the aperture of the telescope, of 200 millimeters. And the focal length, which is what we're interested in here right now, is 1200 millimeters. Just put that number aside and tuck that number in your memory for a second. Here's a big Dobsonian. I can't read it, but I think this is an 8-inch Dobsonian. And so the focal length here, which is written here, would be 2030 millimeters. What you do is you take the focal length of your telescope and you divide the focal length of the eyepiece into that number, and that will give you the magnification. The easy example is right here with easy numbers. If your telescope is 1,000 millimeters long, the focal length is 1,000 millimeters, you divide by a 10 millimeter eyepiece, you get 100 times magnification. And so it's really simple to figure that out. And so then there's a concept of maximum magnification. Well, maximum magnification, it has to do with two things. One is the size of your telescope. The other is the atmosphere. So let's talk about the size of your telescope first. Again, the simple rule of thumb of how much maximum magnification you can use with your telescope before the image starts to degrade, before the view actually gets worse as the thing, whatever you're looking at, whether it's the moon or a planet or whatever, it will get worse and worse if you exceed the maximum magnification of your telescope. The formula is you can be expressed in two ways. It's either you do inches times 50. So here's 4 inches times 50 is 200. Or you have, here's another example, 6 inches times 50 is 300. And then you've also got the aperture of the scope in millimeters. So 4-inch scope is 102 millimeters, and you multiply that by 2 to get that same 200. Here's an 8-inch telescope, which is 203 millimeters. Multiply that by 2, and you get about 400 times magnification. Now that's all well and good, but the more important factor of how much your maximum magnification will be is related to your local seeing conditions. I'm going to talk about seeing in a moment. But what we've got here on the Front Range is we're in a really bad location for magnification. We're in a great location for dark skies. We have a mile less of atmosphere above our heads, and that means that the atmosphere is darker. But put aside dark or clear, put aside those concepts for a second, and what I'm going to talk to you about is a concept known as stability and instability, or also called turbulence. And so here, we're on the wrong side of the Rocky Mountains. And that means that because the wind is whipping through those mountain passes, Berthoud Pass and Loveland Pass, that you hear on the weather reports all the time, because the wind is whipping through there, we have very turbulent air here. This is the same turbulence that you might experience when you're flying in a plane. You're flying along, and all of a sudden, out of nowhere, you just start bouncing all over the place. We have a lot of that here on the east side of the Rockies. And that means that the amount of magnification that we can use is decreased. An analogy for this is that when you, let's say you and I are standing by a swimming pool, and I throw a coin into the swimming pool, and the coin floats down to the bottom of the swimming pool, and I turn to you and I say, all right, what coin is that? You're not going to be able to identify the coin. Why? Because the surface of the pool is now full of ripples from my having thrown the coin in. And so you can't identify what coin it is, whether it's a quarter, nickel, or dime. You can't tell if it's heads or tails. You can't tell if it's an American coin or a Canadian coin. You can't tell any of this information just because of the rippling of the surface of the pool. Here on the Front Range, we live under a swimming pool of atmosphere that is rippling all the time. Sometimes, a few times a year, maybe a handful of nights all year long, the atmosphere is going to go real nice and quiet. And this concept is called seeing. And what I mean by that is we have the jet stream here. The jet stream is usually above Colorado, unfortunately. Sometimes the jet stream decides to move up to Wyoming. And I wish it would make a permanent move there and settle down, but unfortunately it doesn't. But the jet stream is causing a lot of that turbulence. Another thing that causes turbulence is if you're looking at something that's relatively low in the sky and you're looking over the rooftops of neighboring people's homes, there's going to be heat rising off of these roofs, and it's going to lead to bad seeing. You always want to try to look at something when it's as high in the sky as possible. Obviously, sometimes that can't be helped, and you just have to sort of suffer through the view of when something is right above someone else's rooftop. But the roof it absorbs heat all day, gives it off slowly at night, And so you want to try to avoid looking at something right over someone else's roof, if that's possible. When you go outside and you see Twinkle, Twinkle, Little Star, that's not a good thing. It's a cute song, it's a lovely poem, but it means that the atmosphere is very unstable. And so when the atmosphere is unstable, it's like those ripples on the surface of the pool. And that's going to rob you of the ability to use magnification. So here on the Front Range, we're generally limited to roughly between 150 to 175 times magnification on an average night. There are certain above average nights you can push it to 200 times magnification. And this is irrespective of the size of the scope, as long as the scope is 4 inches of aperture or greater. So a 4-inch scope, 5-inch scope, 8-inch scope, 10-inch scope, it doesn't matter what the aperture of the scope is. You are only going to be able to get up to about 150 to 175 times magnification. On those very small handful of nights all year long, about 3 nights, 5 nights, it just depends. The atmosphere is going to go real quiet. The jet stream is going to move up to Wyoming. All the stars are going to align, pun intended, for you to have just really beautiful, steady air above you. Again, this has nothing to do with how clear it is. Clear is great. We love clear. But actually, some of the steadier nights are nights when there are actually a few clouds in the sky and the clouds aren't whipping along. And so when you go out and you see that it's not Twinkle, Twinkle, Little Star, that you're getting a very steady amount of light from the stars, then those are the nights when you're really going to pump up the magnification. Go to 200, go to 250 if you can. Try even 300. If your telescope is 6 inches or greater, you could go to 300 and see if you can get a decent view. And so when you bump up the magnification like that, you're going to be testing the limits of the atmosphere. Now, put aside everything I just said about seeing. Whenever you're out with your telescope and you're looking at the moon and the planets and you want to get a high magnification to see as much detail as possible, forget everything I said, try your high magnification eyepiece anyway, and maybe it'll work for you, and maybe you're going to be able to get to 200 or 250 times magnification, and that you'll say, oh, that guy John, he doesn't know beans. Great, I'm happy for you if you can push the magnification up that far. But my experience is that it just doesn't go up that far on most nights. Here's a difference between Jupiter on a night of good seeing and a night of poor seeing. Now let's take a step back for a second. On the right, you're never really going to be able to see Jupiter with that much detail because, first of all, through a telescope, it's just not going to be that size. You're not going to see Jupiter that large. Whether you're at 200 times magnification, 300 times magnification, 400 times magnification, you can never see Jupiter as big as it's shown here. But what I want you to do is just look at the level of detail between these two photographs. You've got the great red spot over here on the right limb of this right picture. There's the great red spot. You've got one of the equatorial belts here. This must have been a time when the other equatorial belt was a little bit faded away, but usually you can see 2 of them, one here and one here. Sometimes those equatorial belts do disappear or at least fade away for a time, so it's fun to look at. And so here you're seeing the effects of unsteady air. The air is blurry. The view is blurry because the air is turbulent. And this is the level, this is just an example to show you of what happens when the seeing isn't as good. You can still see some detail here. You can still see the equatorial bands, these 2 right here. You can see additional bands beyond the first one. Here's one here, here's one here. You can see other features in Jupiter. This is actually not on Jupiter itself. This is actually a moon. And this is the moon's shadow. So take a step back for a second. I just want to share with you one of my favorite things to look at. Whenever you look at anything in the sky, whether it's the Great Orion Nebula or the Hercules Cluster or M92 or Andromeda, you will always see it looking basically exactly the same with very, very few exceptions, unless there's like a supernova in Andromeda, which might happen, or something like that. You're basically always going to see it the same. Now, you will have changed. Your conditions may have changed in terms of how steady or clear the sky is. Your telescope may have changed, but whatever you're looking at is going to be the same. With Jupiter, you're entitled to a little bit of a treat. Every couple of days, the 4 Galilean moons of Jupiter, and this is one of them right here, this bright spot here, will pass directly in between the Earth and Jupiter, and you'll be able to see the shadow of that moon transit across the face of Jupiter. And here's that shadow. And with even a 4-inch telescope, you're going to be able to see this tiny shadow, which is only about 2,000 miles wide, and it's about 500 million miles away. And it's pretty amazing that you can see it move in real time. If you take your telescope out, you can find tables of when these moon shadow transits will occur. If you just type that into Google and Google that, you'll see when they occur. They occur every few days, but every few days means, well, sometimes it's occurring that we'll be able to see it here in the Western Hemisphere. Sometimes they're occurring, we'll only be able to see them if you're in Japan or South America or wherever. And so you might not be able to see them from Denver every few days. Sometimes every few days it gets cloudy and you're clouded out. But you can reliably count on once every couple of weeks, it'll be clear enough and it'll be the right time of night, 10 p.m. as opposed to 3 a.m., where you're going to be able to see a moon shadow transit. There are also double moon shadow transits where you see 2 moons going across the face of Jupiter, which is even cooler. And if you're out there with a group of, say, 4 people observing with your telescope, and each person takes a look. So you look for a minute and you go, wow, it's really neat. And you pass along to the next person and the next person and the next person. By the time it gets back to you, after going through a few people, you will have noticed that it's moved. Now, it's not moving fast enough where you can just sit there and look at it. It's really slow. But if you look at it and then you wait 5 or 10 minutes and you look at it again, you are going to be able to see it move. So it's a very cool thing to see. Here's again another, this is more about the size of what Jupiter would be, and about really more this size on the left. This is about the size of Jupiter in a telescope. Again, you can see a good bit of detail in here. You see the 2 equatorial bands. You see it maybe the hints of a 3rd and 4th one at the top and bottom here. On a really outstanding night, you'd be able to see Jupiter like this and see there's like modeling in the bands. And you see the gap where the great red spot is in the band. And you'd be able to see this level of detail on the right. And yes, it's bigger. I tried to get something where it was the same size, but I couldn't quite do it. But yes, but the idea here is this one's just a little bit blurrier. Here's Mars. Don't look so much at the surface of Mars. You're seeing some dark modeled features here. What I want you to pay attention is the edge. So the edge here of Mars is sharp. Here, it's sort of just fading away. And that's not because of Mars's atmosphere or anything. The seeing on this side on the right was just worse than the seeing on the left. So it pays off to look at the planets, the moon and planets on different nights and see if you can tease out a little more detail than you saw on a previous night. Let's talk about eyepieces. One aspect of eyepieces is a feature called eye relief. Now we talked about magnification and how you'd calculate that. Eye relief is the distance that you can keep your eye, the lens of your eye, from the lens of the eyepiece and still take in the entire view that the eyepiece has to offer you. Now, I want you to imagine for a second that you are at the eyepiece of your telescope, but your head is 6 inches away from the eyepiece of your telescope, and you try to look through the eyepiece from 6 inches away. If you tried to do that, what you would see is you'd only see a little tunnel view of what the eyepiece could offer you. You know that if you moved the eyepiece, you moved your head closer to the eyepiece, that the view would widen out as you did that. Eye relief refers to the maximum distance that you can keep the lens of your eye from the lens of the top lens of the eyepiece and still see that maximum view that the eyepiece can offer you. Now, there's a couple of reasons why eye relief is important. One is if you wear glasses and you need to use your glasses while you observe. So let's take a step back there. Most people do not need to use their glasses when they observe. You can take your glasses off and you can just change the focus on the telescope, let the telescope replace your glasses. So if you don't have astigmatism, if you're just nearsighted or farsighted, you can let the telescope replace your glasses. You'll have a different focus point than someone else who's observing with you, but that's fine. They'll just change the focus a little bit to their focal point, and they can observe with a sharp focus with them. However, if you have astigmatism, that means that you have a defect in some portion of the lens of your eye. There's something wrong, and your glasses are built to correct for that astigmatism. If you have only a mild or minor astigmatism, try observing without your glasses. That way you'll be able to get your eye closer to the lens and see more. But if you need to use your glasses to correct the astigmatism, if the view looks terrible without your glasses and you can't focus it to get it any better, you need to use your glasses, then you need to buy an eyepiece with long eye relief. And what that means is you've got to have about 15 millimeters of eye relief, and it's a specification. If you go onto any website that sells eyepieces, whether it's Mile High Astronomy or High Point Scientific or Adorama or any of the retailers, they will have a specifications area for every eyepiece. And you can click on that and you can get what's called the eye relief for that particular eyepiece. You need to have, if you need to use your glasses while you are looking through the eyepiece, you need to have at least 15 millimeters of eye relief. And that means that you're going to have your glasses. Here's a picture with the glasses in between. You're seeing a cutaway here. And so you need to have additional distance. People without glasses, they could get their eyeball closer. They'll be closer to the eye, to the top lens of the eyepiece. But with the glasses, you need to have that additional distance. And the 15 millimeters is a minimum. 16 is better, 17 is better. And so these eyepieces, unfortunately, they cost more because they're engineered for people who need to use their glasses when they observe. So when you're picking additional eyepieces for your telescope, one factor is to consider is whether or not you need the additional eye relief. Another factor is that you want to have a spread of about 3 or 4 eyepieces for different purposes. Most telescopes will come with 2 eyepieces. So this example is for a 1200 millimeter telescope. And I'm going to keep on using that as the example. The reason I use that as the example is that a 6-inch Dobsonian or an 8-inch Dobsonian, both of those 2 telescopes have a 1200 millimeter focal length. So we're going to use the math here. And a 6-inch or an 8-inch Dobsonian will come with 25 millimeter and a 10 millimeter eyepiece. So 2 eyepieces. And the 25 millimeter is going to give you a nice low magnification of 48 times. A 10 millimeter is going to give you a high magnification of 120 times. Now, that's a really good place to start. And between the 2 eyepieces, you can really sort of use them, enjoy them, understand how they work, understand what you'll see with each of them. And what you need to do is you need to question authority. You need to do this in your life, but you need to do this with your eyepieces. You need to say, okay, I like this 25 millimeter eyepiece. I like that it does this, but can it also do that? Can it do additional things? And what I mean by that is, well, can I get a lower magnification that's going to give me a wider field of view? By wider field of view, again, we're going to go back to the example of the moon being a ½ degree across. With a high magnification eyepiece, like a 10 millimeter, you won't be able to see the moon all in one view. You're sort of zoomed in. As you can imagine, you see all the moon when you're at a low magnification. And then when you switch to a high magnification, you won't be able to see the entire moon with the stock eyepieces that come with the telescope. Well, when you've got a lower magnification eyepiece, generally speaking, a 40 millimeter Plössl, as an example, will give you the widest field of view possible in a 1 1/4 inch eyepiece format. Eyepieces come in 2 formats. One is 1 1/4 inch, and this is the size of the barrel of the eyepiece. If you want to take a break right now and just walk away from the computer, go pick up your eyepiece, you could measure that size of the barrel, and you'll see that it's 1 1/4 inches across. And then there's also another magnification called a 2-inch eyepiece. And we'll get to that in a second. But here's a low magnification eyepiece, 30 times is lower than 48. I'm going to keep on using this 1200 millimeter telescope as the example. Your mileage will vary depending on your focal length. But I can't go through all the different focal lengths. I'm just going to stick with this one because it's a popular design. You could also go higher magnification. There's an eyepiece called the 7 millimeter XL-LX eyepiece. And that will give you 171 times magnification. That's going to be about the maximum magnification here on the front range. And then you've got even a 14 millimeter eyepiece. That's going to give you a medium magnification, but it's going to give you a really wide field of view with 82 degrees of field of view. Most eyepieces that come with stock with telescopes are going to have about a 50 degree field of view. The ones that come with the telescope originally have a 50 degree field of view. And the way to think about that is just to think about an angle coming out of your eye, and covers 50 degrees. And if you think of that as going out to 82 degrees, that's a lot wider. So at the same magnification, you can get, for example, a 10 millimeter eyepiece that has an 82 degree field of view. It's going to give you the exact same magnification, 120 times magnification that the stock eyepiece with your telescope will give you, but it's going to give you a much wider field of view because these eyepieces have about a 50 degree field of view. You can get in a much wider field of view at 82 degrees. So we're going to talk about why you'd want to do this. There are things that will be really much more pleasant to look at with a wide field of view, like, for example, M81 and M82, which are a pair of galaxies in Ursa Major. That's a Big Dipper. There's also the Leo triplet, a triplet of galaxies. And these are things you can see all in the same view, but only if you have a wide enough field eyepiece. And so you can see them in the same view, probably with the 25 millimeter eyepiece. But if you want to bump the magnification up and almost double it, you go to 14 millimeters or something like that. And so that's a way to see more in one field of view at the same magnification. An easy way to increase magnification would be to get a Barlow. I'm going to talk about the Celestron. There are other models that do a similar thing that this one does. So you see this Barlow here, there's a black part on top. Instead of putting your eyepiece directly into the focuser of your telescope, you want to put the eyepiece into this part of the Barlow. Then tighten down this thumb screw here, and this becomes one unit of a Barlow with an eyepiece in it, and put the pair of them into your telescope together. This is a 2x Barlow lens. Most Barlows are two times, but there are plenty of other magnification Barlows. And what the 2x Barlow lens does is it just doubles the magnification of the eyepiece that you put in there. So for example, you have a 25 millimeter and a 10 millimeter. You would double that, you'd get 96 times magnification. And so the 25 millimeter eyepiece becomes effectively a 12.5 millimeter eyepiece. With a 10 millimeter eyepiece, you would divide that by 2, and that gives you a 5 millimeter eyepiece. I know that sounds counterintuitive, but the lower the number eyepiece, the higher the magnification. And this is going to give you 240 times magnification. Now, again, like we discussed, that's probably too much magnification for here on the Front Range here in Denver. However, there are other locations in the country. If you take your telescope with you someplace, there are different seeing conditions in different parts of the country. And this is going to give you a different magnification, a different level. For example, this Barlow has a neat little trick. Right down here, this is just that empty tube, this part. This silver part on top, this gray part on top, the silver part in the middle is just empty. That's just empty space. Down here, these are the lens elements. What you can do is you can unscrew this part off of the Barlow, screw this part directly onto the bottom of your eyepiece. Everything's threaded the same way, and you can get an intermediate magnification of about 1.5x. So that would give you, with the 25 millimeter, 72 times magnification. With a 10 millimeter, you can get 180 times magnification. And that'd be nice to have. If the seeing is a little bit above average, you could push the magnification to 180 times magnification. So a Barlow is a nice thing to have in your eyepiece box as something that you could use for different conditions in the sky. Let's talk about, as long as we're talking about Dobsonians, let's talk about adjusting them. You can adjust your Dobsonian. This is the rocker box at the bottom beneath where the tube of the Dobsonian goes. There's a little screw down here, and there's a screw on the bottom of the Dobsonian too, underneath the two discs of the Dobsonian. If you take 2 wrenches, you can adjust the tightness of these screws. If your Dobsonian is moving too stiff or too loose, you can tension this down or tension this up to change how easily or how difficult it is to move your Dob around. And there are also tension knobs on either side of the Dobsonian as well. You can tighten these down or loosen them up, and that will tell you how easy or hard it is to change the altitude up and down of the telescope as well. So it's a nice little trick. Some telescopes, some tripods have what are called slow motion controls. Not all do, but some do. Your telescope may have these. And these slow motion controls are great for when you need to track the object. So as you look through the eyepiece, if you've ever looked through the eyepiece of a telescope, you'll know that whatever you're looking at is going to be moving slowly across the field of view. you can use these slow motion controls and turn them the opposite direction and keep that object from moving out of the field of view and move it back into the field of view. And these slow motion controls are really good for doing that. So what you want to also consider is having the low magnification. So the low magnification, we're talking about high magnification, and of course everyone wants high magnification. You want to see the most detail on the moon. You want to feel like you're, in a spacecraft floating around the moon in orbit. You want to get as close as possible to the planets of Jupiter and Saturn. That's great. Everyone loves high magnification. But there's a point and a purpose for low magnification too, which is that this low magnification eyepiece is going to give you the widest field of view possible in your telescope. And we call that a finder eyepiece. And by finder eyepiece, what that means is that you're going to use this eyepiece when you're first looking for an object. It's like looking at an object through a toilet paper roll tube, which is nice and wide, as opposed to a straw, which is really narrow. It's much easier to find something through that toilet paper roll tube. And the low magnification eyepiece, your lowest magnification, is going to be able to let you do that. So let's talk about field of view. When you have the stock eyepieces that come with the telescope, here's the Orion Nebula, and it doesn't really look like this. I'll explain that in a moment. The stock eyepieces, you might crowd the Orion Nebula so that you're not seeing it in the context of what its surroundings are. So you're just seeing your entire field of view is filled with nebula. Now, some people might like that. I like to see things, it's more aesthetically pleasing. And notice that these are the same size. The nebula hasn't changed size. It's the same magnification. You're seeing more of a patch of sky with a wider field of view eyepiece. So this might be a 50-degree field of view here. This would be an 82-degree field of view here. For my money, I think this is a more pleasing view on the right than on the left. Here's a galaxy, and galaxies, unfortunately, really do. Many of them look just like this, just sort of a fuzz patch. And so this actually has been enlarged. This is the same picture. One of them is bigger, and you're seeing the bigger galaxy here. The idea is pretend this is the same size, and this would be a 50-degree. This would be an 82-degree field of view. And so it's just nicer to see that way. So then what can you really expect to see? Well, here's the Orion Nebula again. This is a lovely astrophoto of the Orion Nebula, and you're never, ever, ever going to see that through your telescope. Sorry to burst your bubble there. It doesn't look like this. There's almost no color in space unless you have a 20 or 30-inch telescope. And most of us don't, and at least hopefully the people who are on this Zoom call, this Zoom meeting, wouldn't have that, or else you wouldn't be here. You're starting out with a small telescope, whether it's 4 inches or 6 inches, or even a medium-sized telescope, an 8-inch telescope, and you're still not going to be able to see this color here. You're also not going to be able to see as much detail. And this is the same, basically the same relative size. You see these 3 stars here. There are those 3 stars right there. This little tight bunch of stars is barely, it looks like sort of a blob, is right here. And that's called the trapezium. You can see basically this amount of detail, I would say with maybe an 8-inch telescope on with a dark sky. Not necessarily, out at the dark sky site that the club has, but you can see something like this 8 inches, maybe a little bit closer into town. And so there's really almost no color in space. There's no color really in this nebula that your eyes can pick up. And there's no color basically in most things that you're going to be looking at, with a very few exceptions. One of the exceptions is the planets. Jupiter has a sort of yellowish tinge. The red spot could be sort of red. It looks sort of brownish. Saturn is very strikingly yellow. Mars is definitely an orangey red. So you can see significant color in the planets. The moon is actually, in real life, if you were walking on the surface of the moon, if you've seen the astronauts do that, the moon is just gray. So, you would be able to see color on the moon if there were color on the moon. Unfortunately, there is no color on the moon to see because the moon is plenty bright enough. But then you've got things called double stars, and double stars will also have significant amount of color in them. We'll get to that in a moment. You've got a red light here, and here's another one. This is a red flashlight. One of the things you want to do is just a tip, is that you want to be able to look at things on a map or on your list. Maybe you made an observing list. You need to look something up. And what you do for that is you don't use a white light. You use a red light. Red light is not going to affect your dark adaptation. So when you go outside, it's going to take you a number of minutes to get dark adapted. And that's going to occur over 5 minutes, 10 minutes, 15 minutes. The longer that you're out in the dark and you're not looking at white light, meaning the white lights from your neighbor's house, the white lights from headlights of cars going along the street, the white lights of street lights, as long as you're avoiding any white light, you're going to be able to dark adapt and see much more dim objects, whether it's with your naked eye or through a telescope. A red light will not affect that dark adaptation very much, and that's what you want to use. A headlamp like this is going to let you keep your hands free, and this is what I use. But you can just take a flashlight. If you have red nail polish, you want to coat the lens, you can do that too. But I prefer the headlamp. Dark adaptation is important. You want to eat your carrots and get that vitamin A in your eyes. People who don't have enough vitamin A have a little bit of night blindness, and anything with beta carotene is going to give you a nice boost to your vitamin A level, and you're going to be able to see more. Like I mentioned, you want to avoid white light, especially from your phone. It's so easy to take out your phone and play with your phone for a moment. As soon as you see white light for 1/10 of a second, all that 5 minutes, 10 minutes, 20 minutes, you will increase up until about a half an hour with diminishing returns of getting dark adapted and being able to see more and more. All of that 20, 30 minutes will be wiped out instantly with 1/10 of a second of white light from your phone. The longer that you're away from white light, the more you'll see. But again, it's a diminishing returns. Basically, after 15 minutes, that's about what you'll see. You will see a little more after 20 or 30, but 15 minutes is a good cutoff. And you want to keep away from that white light as much as possible. One way to do that is with an eye patch. So you can keep the eye, you basically will have one dominant eye that you're going to look through the telescope with. You have to figure that out for yourself, whichever eye works better for you. An eye patch will keep that eye away from white light, and you can remove the eye patch just when you're about to look through the eyepiece of the telescope and keep it dark adapted the entire time, and use the other eye. The dark adaptation is different for each of your eyes, believe it or not. So this eye can be flooded with white light, and as long as this eye's in the dark, you're going to be in good shape and you're going to be able to see more with it. Then there's things called observing chairs. These are not really for your legs or for your butt. They're actually for your eyes, believe it or not. And the reason is that, yeah, it is nice to sit down, and especially when you're at a certain age, like many of us in the DAS are, it's more comfortable, and it just takes a load off to sit down and observe as opposed to standing up or bending over in an awkward position. Sometimes the eyepiece is a little bit lower than you might like. And these are adjustable chairs. This one is the Starbound. The Vestal is very similar to what we see pictured here. There's also something called the drummer's throne, and this is just what it sounds like. It's what a drummer in a band will sit on, and it has the seat that is adjustable if you give it a spin. There's also something called the Denver chair, and it has nothing to do with the fact that we're in Denver. It's just the name of the actual chair, where the seat adjusts up and down. And these are really good for your eyes. What I mean by that is, if you're comfortable, you will observe longer. When you observe longer, you see more. And you see more because it does take a few seconds for your eyes to adjust to looking through the eyepiece. It does take a few seconds for you to lock onto the object and look around at the object and see all the different things that the object is presenting to you. And as you observe longer, there's a difference between looking at an object and observing an object. If you look at an object, then that's fine. And I'm not making any judgments. People look and people observe. It's up to you what you want to do. If you look at an object, you're looking at it for 30 seconds, 45 seconds, and that's fine. If you want to observe for like 5 minutes or 10 minutes, a chair is going to let you do that. Why would you want to observe as opposed to just look? The reason for observing is that you will be looking at the object while the atmosphere is changing above your head. So the atmosphere, that instability in the atmosphere, that bad seeing that we have, it's not bad seeing, 24/7. It's not bad seeing every second of the day. And so for a few seconds, every few minutes, the atmosphere may, if you're lucky, quiet down, get nice and stable above your head for just that little brief window of time. And when that happens, the details on the object are just going to go wah and pop into view. You're going to see all this detail on Jupiter. You're going to be able to split the, say, the Cassini division and see instead of one ring of Saturn, you'll see two rings of Saturn. You're going to be able to see tiny little craters on the moon where you couldn't see anything before will now be visible to you. And so it's not predictable. It's random. The longer you observe, the more you'll see in terms of this little window of clear seeing of stable air. But it's not guaranteed either. You could be sitting there at the eyepiece for 10 minutes, and unfortunately, you didn't see anything more than you saw when you started it, 10 minutes ago. But the observing chair will let you at least test that out, at least give you a chance to be rested, relaxed, and see more. So what is there to see? Well, the best object, in my view, to see is the moon. Why? Because half of the time, half of the nights, the moon is up and is probably ruining your view of everything else. So you have to fall in love with the moon. If you don't fall in love with the moon, you're just going to have a tough time in astronomy. By that, you really, because the moon is so bright, it creates its own light pollution. Here in the Denver metro area, we've got plenty of light pollution from all the people who have their bedroom lights on, they have their car lights on the highways, there are street lights that never go out, and all of this is causing light pollution. And the moon causes light pollution too, but it's unaffected by the light pollution as the planets are. The planets are unaffected by light pollution as well. And so you really have to learn to love the moon and get to know the moon. Here's the moon in different phases. And when the moon goes through different phases, you see different things. Here I'm seeing some craters and such, some seas and some detail in the mountain ranges that I can't see at an earlier phase. I'm seeing this is one eye of the moon, this is the other eye of the moon, and I'm seeing this whole range, this mountain range that is here and invisible earlier on. So you can, look at the moon every 2-3 days, and it's always going to present something new to you. Here's a field of craters. I'm going to talk about this particular one in just a little bit. One thing that you want to think about when you're looking at the moon is using a moon filter. The reason is because the moon is so overwhelmingly bright that it's just going to blast your eyes, and it's going to be like someone took a picture of you with their cell phone and the flash went off and you're blinded for a second. A moon filter, whether it is a fixed moon filter, which is just like sunglasses. If you've ever worn sunglasses, your sunglasses let in a certain amount of light and block a certain amount of light, and they're not adjustable. That's fine. This is going to work really well. You want to look for a moon filter that has a neutral density of 13% transmission, and it's also known as ND 0.9. And so that is a really good filter to use on the moon. Or you can get a polarizing filter that varies all the way from 1 to 40%. It's two pieces. See, there's two pieces here, and you twist one of them while you keep the other one stable, and you're going to be able to adjust the amount of light that comes anywhere from 1%, which is really dim, up to 40%, which is fairly bright, and everywhere in between, any amount of light that you like. So the moon goes through phases. The moon does get brighter. The surface of the moon gets brighter as the phases change, and 13% might be letting in too much light on one night and too little light on another night. And so with a polarizing filter, you can just adjust that to whatever level is comfortable for you. These will screw onto the bottom of an eyepiece. Everything is threaded the same way, and it doesn't have to be celestron to celestron. Even Orion, Meade, Skywatcher eyepieces, Teleview eyepieces, everything is threaded to accept accessories like filters and like a moon filter, and will thread into the bottom of the eyepiece that way. You can also, if you want, you can do what's called a blink, which means you hold these the polarizing filter or the neutral density filter in your fingers between your thumb and forefinger, and you just put it at the very top of the eyepiece between your eye and the top lens of your eyepiece. You can do it that way. There's no eyepiece police who are going to write you a ticket or haul you away for doing that. The best thing about the moon is to learn about the moon. I mean, so here's this beautiful field of craters, and that's really nice, but what am I seeing here? I mean, this is lovely, but so what? The best way is if you learn about the moon and you learn about craters, and here on the back, it has certain different things that you can look for and look at. One is right here, which I'll explain in a moment. Some craters are better than other craters, and some things are more interesting to look at on the moon than other things. And a moon map, a good moon map, is going to be able to show you those things. So for example, this right here, this feature is really easy to see in any telescope at a basically a medium or high magnification, anywhere from about, say, about 75 times magnification up to 150. This is called the straight wall. And this is actually, it's not a wall. It seems like it's a wall and it looks like it's a wall. It's actually a gradual slope of it, but it has an incline of about 20%. And it is this beautiful feature that you can see on the moon. And it's also known as Rupus Recta in Latin. This is a crater called Copernicus, which is located here on the moon. And you can see this is called terracing. You're looking pretty much almost directly down into the crater. Some craters, there's more of an angle and you're not looking straight down into them. With Copernicus, you're practically looking, it's almost at the equator of the moon, and you're looking just straight down in, and you can see all the features of the walls. I mean, this is really, even though this is a photograph, you can really see this much detail on the moon. You can see this chain. Here's a chain of craters here from just battered the moon all in this long line. And you can see that on good nights. You've got this crater here is called Clavius crater. This was in that view I showed you here. And so there's Clavius crater. It's also down here as well. It's down towards the southern pole of the moon. And what do we have here? Look at this. You have, it looks like someone took a stone and skipped it on a lake and made all these craters going around almost 180 degrees, starting here and going all the way around. And that's just an incredible sight to see. For those people who are movie buffs, the movie 2001, A Space Odyssey, the base was at Clavius crater. Talk about double stars, another thing to see. Here's a few, but what you're looking at with double stars usually is these beautiful colors and a contrast in the colors of the double stars. So you have a few different ones here that are really lovely. Mizar and Alcor are widely separated. You can look at those two with your naked eye and see if you can split them with your naked eye. You've got open clusters. They're fun to look at. Here are the Pleiades, which are very large on the sky, as well as the double cluster. And again, these objects do actually look very much like their photographs, that they're going to look a lot like this when you look at them through the telescope. This one is called the Wild Duck cluster. It looks like a globular cluster, which I'll talk about in just a moment, but it's not. It's an open cluster. Open cluster refers to that these are just stars that just happen to be right next to each other that formed from the same dust cloud and were born basically at the same time and are traveling in the same direction, but they're not gravitationally bound to each other as much as globular clusters. And that is a glob. You could think of a globe being a ball of stars. This one here is M13. This one here is M22. These are just fantastic objects. These are starting to not look quite as much like what they look like through a telescope. Through a very large telescope, you're going to see a lot of individual stars. By very large telescope, I'm talking about an 8-inch, a 10-inch, a 12-inch telescope. You can break out the individual stars in these globular clusters. But with a smaller telescope of 4 or 5, you see more of a haze, a fuzz of stars in the center, and towards the edges is where you start seeing the individual stars. Then you've got diffuse nebula. So here's the Orion Nebula right here. And you're seeing, this is that trapezium I mentioned before, and those 3 stars in a row. And this is a feature of the Orion Nebula called the fish's mouth. Here's one. These two are drawings. And I picked drawings specifically because the photos don't look like what you see at the eyepiece. The photos are in color. They're beautiful. They're gorgeous. They're stunning. But this is something called the Swan Nebula. You see here's the head and neck of the swan, and it's swimming along. Also called the Omega Nebula, sort of the shape of the Greek letter omega. It's also just the number 2. This is something called the Trifid Nebula. You see there's 3 lobes. There's dark lanes here. And you can see this with a telescope under dark skies. And these are nebula, and you would be able to see these objects with even a relatively small telescope of about 4 or 5 inches. Planetary nebula are fun to look at. These are the remains of a star that has died. And these aren't supernovas, these are novas. Our sun is going to look like this in about 5 billion years when our sun dies. This one here is called the Ring Nebula, and it's this tiny little puff cloud of smoke. And you can barely make out the center as being empty. And right here, I don't know if you can see it on your screens, there is a center star to it. Here, the center star is obscured, the star that died. This is the star that died right here, if you can make it out. But here, the center star is obscured by the dust in the middle. And so this is called the Dumbbell Nebula. It's also called the Apple Core Nebula. It looks like an apple that someone has taken bites out on either side, or a dumbbell. You see these are the weights on left and right, and this is the bar in the middle. And these are very simple, just very easy to look at, and they do look remarkably like the photographs. Galaxies kind of don't. So here's the Andromeda Galaxy down here, and it takes a very small telescope at very low power to get the whole galaxy all in one view. Right here, you might be able to see these are dust lanes. These dust lanes are very difficult to pick up because the surface brightness of galaxies is very low. But you've got two in a view with M81 and M82. These are two galaxies in Ursa Major, Big Dipper I mentioned earlier. This is called the Leo triplet here. You can see three galaxies all in one view. You need at least about a 6-inch telescope to catch all three. 5-inch telescope will catch two of them, and the third one will be really difficult to spot. M81 and M82 are very easy to see with almost any size telescope. And you would look at a star chart or punch it into your hand controller to view objects like this. There's also something called the Virgo cluster, which is just about a dozen galaxies, and you can spend an evening just looking at a dozen different galaxies. But they look like these gray fuzzy patches with not much detail. You might be able to see some modeling, some of the dust lanes in some of these galaxies. But that's something that you really need good conditions, good eyes. You need to train yourself, and you need to observe rather than view. You need to look at it for a few minutes. Now you notice that these two were called M81 and M82. Two of these galaxies, one of them is M64 and M65. And the M stands for Messier. And this is Charles Messier here. He was a French astronomer in the late 1700s and early 1800s. He observed for Napoleon and tried to curry favor with him by, naming comets after him. And he was on the very end of the time period when comets were considered to be portents of the future. Like, oh no, there's a comet in the sky. This is going to be bad. The crop's going to fail. There's going to be war. Who knows what's going to happen? They thought comets really were a sign that something bad was going to happen. And then he was at the very end of that period before people said, no, that's BS, that's crap. Don't believe in that anymore. But he would try to curry favor with the rulers of France and say, hey, let me name a comet after you. What Charles Messier was doing is he was looking for comets. And so what he did was he just patrolled around the sky and said, all right, here's something that looks like a comet. Not a comet. Let me write that down and mark its location so I know not to get confused by this object ever again. And he made a list of 100, it turned out to be a total of 110 objects that he said aren't comets. And he had no interest in them because they were just there, not doing anything, not moving, just the same object year after year, and always annoying him and getting in his way and saying, oh, wait, is that the comet? Oh, no, I found that one already. That's one of those, that's not a comet. And so he made this list of things that aren't comets. And this list is a terrific list. And we ignore Messier's advice of looking for comets or looking for comets. We instead look at his list of things not to look at. He is spinning in his grave at a rapid pace because his list are most, not all, most of the greatest, most beautiful objects in the sky are on his list of the Messier catalog. Let's talk about telescope cleaning briefly. You definitely don't want to do it. If you think you might want to do it, give me a call at the store. I'll talk you down from the ledge. This is a relatively, even you see dust on it, this is a very clean mirror right here, and you wouldn't want to clean this. Even though you see specks of dust on this corrector plate, this is relatively clean. It's not clean, but it's definitely clean enough, and you don't want to clean this. It's got to be, and this is a really clean, this is a perfectly clean, a corrector plate on a Schmidt Cassegrain. Obviously, you're not cleaning that. But the point is, you have to get to something even worse than this before you'd even consider cleaning your optics. The reason why you don't want to clean your optics is that when you do, as a novice, no matter how careful you are, there is a chance that you're going to scratch up your optics. And what dirt, what dust, what something on the optics will do is they're just going to block a tiny, tiny, tiny fraction of the light that's getting through. Even something as dirty as this, you're losing maybe 1 or 2% of the light that would otherwise come through this particular piece of glass. You don't need to clean that. And I'll tell you why in a moment. Because here's the McDonald Observatory in West Texas. This is a 107-inch reflector. And look over here. See these big black dots? Unfortunately, one of the employees at the McDonald Observatory went postal, and he shot up the mirror as well as trying to shoot the other employees. He shot up the mirror, and he had 6 bullet holes are visible here. There's a 7th one as well. And look at this. This is terrible, right? And then he took a hammer to the mirror to try to destroy it that way, and that didn't work. And so he shot 7 bullet holes in this mirror, and you know what? Mirror is fine. It has affected the views through the telescope only by, they estimate, approximately 1%. And so please, please don't clean your optics. When a scratch on your optics will cause diffraction of the light. That means the light's going to spread out. It's going to interfere with your view. You're going to lose contrast. A scratch is so much worse than just having a tiny percentage of your view blocked. Having a percentage of your view blocked just means the view is slightly dimmer. And more to the point, the human eye cannot detect differences in light until it hits about 10%. That's way cruddier than this. This is not 10% of the light being blocked. This is maybe 2% maximum. And so you have to rein in your OCD tendencies and just not clean something, even when it's this dirty. If you do decide to clean, don't use Windex, please. It's not designed for optics of the grade of a telescope. What you do want to do is you want to use distilled water. You can buy this at any supermarket. You want to put a drop of Dawn liquid in there. I don't know why it's always Dawn, but it just is. And you want to use cotton balls that are sterile, and you want to use that mixture to dip the cotton ball in, and you're going to wipe it like you remember, if you might remember cleaning CDs 20 years ago. The way you'd clean a CD is you'd clean it radially from the center outward, from the center outward, from the center outward. And what you do is you take the cotton ball, you dip it in the mixture of this. Some people even like to add some rubbing alcohol, 91% isopropyl alcohol to this mix. So it's the water, one drop of Dawn. You don't need a lot of soap, and some isopropyl alcohol, and that helps the water evaporate better without water spots. Anyway, you're going to dip your cotton ball into that mixture. You use one cotton ball, you go from the middle to the edge, throw that cotton ball away. Take another cotton ball, middle to the edge, a little bit off of that line that you just did. Throw that one away. And you keep on doing that over and over, cotton ball, cotton ball, cotton ball, cotton ball. You keep on doing that until you go completely around. Again, I would urge you not to do this because you have a chance of scratching, and scratching is worse. There's also for pollen or for light dust, if you do want to just get things off of your mirror or your corrector plate or your objective lens, depending on what type of telescope, you can use a hurricane blower. That's not going to hurt anything. You can just squeeze this bulb, and you can get this in any camera store, and it's going to shoot out a stream of air, and that's going to clean off whatever your optics are. That's great. That's going to work just fine. And that won't affect anything bad at all. For eyepieces, you want to use something called the lens pen. You're always going to start with the hurricane blower, blow off whatever dust you can blow off, and then you're going to use a brush. This is like a camel's hair brush, which would also work, but this is a very fine brush that does not scratch optics. And you're going to use the brush first, this end here, and you're going to brush off the, if it's pollen, you're going to definitely brush that off of your optics, whether it's a mirror or a corrector plate or the objective lenses of a refractor. You want to get pollen off of your optics because pollen has acids in it that will etch your glass. So if somehow you've left your telescope out and you've left it uncapped, and pollen has gotten onto it, that you definitely forget everything I said about scratching. Pollen's going to be worse. You want to get that pollen off. And so again, you'll start with the blower. You'll move to a camel's hair or a lens pen type of brush. This is marketed under a lot of different names. They all cost about 15 bucks, 12 bucks, somewhere in there. Use this first. Then only for eyepieces, you're going to use this end. Don't use this on your optics of the telescope. So if if someone has put their thumbprint on your on your eyepiece, or if someone has gotten mascara from their eyes onto the eyepiece, you're going to use this end of the lens pen. Again, it's marketed under different names. They all look like this. I'm sure they're all made in the same factory, and they put a different name here. And so this will be able to pick up the oils off from the mascara or from the fingerprint off of your eyepiece. And that's it. That's my presentation. Obviously, I've left out a lot of topics, and I could go on for a long time, but this presentation has a limited amount of time and it has to end. So if you have any questions, definitely feel free to fire away.
Thank you, John. Thank you. This was a very, very detailed and excellent presentation. So thank you very much. I'll ask my question as the first question. I was in Texas before I came here, and we faced the condensations, fogging of the telescopes, especially late at night. And people used to use hair blowers to get rid of the condensation. Can you talk about that condensation of the telescope?
Absolutely. So here in Denver, one of the nice reasons to live in Denver is because we have very low humidity. So here in Denver, dew condensation is generally not a problem, but having said that, there's definitely exceptions. Especially in the wintertime, the atmosphere's ability to hold moisture in it is related to the temperature of the atmosphere. And in winter, it's colder, it can hold less. And when the temperature drops, when you go from daytime to night, there's going to be a significant drop in temperature from, say, the 40s to the 20s. And so what happens is that the dew will form out of the sky, especially in the winter, and that will condense on the front lens of your telescope. If you're using a reflector, if you're using a Newtonian, a Dobsonian, any sort of reflector, that's not going to be that big of a problem because you've got that very long tube in front of the mirror that's going to act as what's called a dew shield. But for refractors have a dew shield built in. That's that part that sticks out in front of the objective lens of the refractor. The compound telescopes, Schmidt-Cassegrains and Maxitovs, they don't have that dew shield at all. So if you have something called like an 8SE or a 127 SLT or something like that, those types of telescopes, the compound, they're also called catadioptric, but I'm just going to keep using the word compound because it's easier. Those telescopes don't have any dew shield. So if you take your telescope away from Denver and you're in Texas, or even here in Denver on occasion, the dew may form on that front lens, whether it's a corrector plate, whatever it is, the front part of your telescope. And that's going to be pretty much the end of the night. Now, like Mehmet said, what some people do is they have a hair dryer, and you can run it on no heat. You don't want to use the heat or put the heat at the very lowest setting, and just sort of blast that over, not directly on, but just across the top of the front lens, and that will help remove the dew. You don't want it on the high heat setting. That's going to be bad for the optics. Don't do that. But you're trying to raise the temperature of the corrector plate at the front of the telescope so that the dew will evaporate. The hairdryer can work. Not a perfect solution, but it definitely can work. The better solution would be to start off with a dew shield. And this is real easy. You can just take some sort of piece of plastic, heavy duty cardboard will work. Something that is basically, cardboard isn't as good because cardboard will get wet, but something where the moisture isn't going to affect it. Roll it up into a tube and you tape that or Velcro that or bungee cord that on the front end of your telescope so that the lens is now buried beneath that tube. And you want to have the length of the tube extend about 1.5 times the aperture of the telescope. So if you have an 8-inch lens, an 8-inch telescope, you want the tube to extend about 12 inches in front. And that will keep most, if not all, of the dew off of your telescope, unless you're observing basically straight up at the zenith, straight up as high in the sky. Then nothing's going to keep the dew from forming down on your telescope. There are also things called dew heater strips. And this is a very low electrical strip of wire. You run a very low amount of electricity through that. The wire heats up. It's protected. It's not a bare naked wire. And you put that at the very front of the telescope. It's in a strip. It's in like a plastic strip. And it has like an adjustable Velcro thing to attach to the front of your scope. And it gives you a very low amount of heat, a continuous low amount of heat that's going to keep your optics from dewing over.
Okay, good. I have some questions coming. By the way, can you stop sharing the screen? Can you turn off?
How do I do that?
Do you
I
know how
will
to do that?
try. Oh, I'm having a little difficult time.
Okay,
with
there is
that.
one question. Are filters for the eyepiece of any real benefit?
Yes, there are some that are definitely of more benefit than others. Hold on, let's see if I can stop.
All the way down to the bottom, John, where it says share screen.
I'm looking for that. I'm not seeing it. Sorry. I don't want to leave the meeting. No. Got my chat here. I don't know what this is going on here.
Sharing. There must be something called sharing, and then stop sharing.
Sorry.
Oh, it's not on your screen.
No, I just took it off. I'm sorry. I can't. Wait, new
Okay.
share. Here we go.
Hit escape.
No,
You need some technical help.
I do. Wait,
It should be on the bottom.
I can do
Yes,
it.
it is at the bottom.
there we go. All right.
Good.
Thank you, Dina. Anyway, yeah, so filters. So the moon filters are the easiest answer to that question is yes, yes, yes. Moon filters will just reduce that overwhelming brightness of the moon. You could totally look at the moon without a moon filter. That's fine. Your eye is going to be overwhelmed. You won't be able to see as much detail. If you reduce that overwhelming brightness, and you'll increase the contrast between the dimmer objects and the brighter objects on the moon, and you're going to see really just a much better view of the moon. So definitely I recommend a moon filter. There are things called light pollution reduction filters. You may have seen these. They're called LPR. That's the initials. You might have seen them. They're also referred to as UHC, ultra high contrast filters. They're also referred to as broadband filters. Unfortunately, these filters are not much use any longer. So I would definitely recommend not getting those. They used to be useful 10 and 15 years ago because what they did is by broadband, what that means is that they're letting through all the colors of light, Roy G. Biv, red, orange, yellow, blue, indigo, violet. They're letting all the colors of light through, except for very narrow slices. Those narrow slices were the sodium vapor, the orange, yellowish orange sickly color of the headlight of the street lights, and the mercury vapor, which is the bluish white. And they would let all the other colors of light would come through, but block those two. Those would be for street lights and also for some car headlights. Great, now you've eliminated a nice chunk of your light pollution very easily. Unfortunately, street lights and headlights have all changed to LED lighting. And LED lighting is what's called full spectrum. It has all the colors of the spectrum are in LED lighting in headlights and streetlights. You can't, if you try to block them out, you're blocking out everything. And so it doesn't work anymore. So light pollution reduction filters are just not as useful.
A comment from Jack, I guess. He says, while a little dirt won't block all that much, it will scatter light and cause a loss of contrast.
Yes, that's true. But I think that it is better to suffer the slings and arrows of a loss of contrast than to have a scratch on your optics. So yes, if you consider yourself extremely, extremely careful and you watch 4 different videos of people telling you how to clean your optics, and you set yourself up in a clean room and you wear your N95 mask and you do all those good things that you need to do, okay, fine, yes, you can go ahead and clean your optics. The best way to have clean optics is not to let them get dirty in the first place. So what I didn't mention is you want to cap off, obviously when you're observing, caps off, everything's fine. You need the caps off to observe. You can't observe with the cap on. When you're done, the very first thing you do when you are packing up is you put that dust cap back on the front of the telescope and you put it on your eyepiece as well. And that will keep it from getting dirty in the first place.
Okay. Any other questions?
Yes.
Yes, Dina.
Mark Chrisman asks, are filters for the eyepiece of any real benefit?
So yeah, so we covered.
I already answered. I already conveyed that question.
Right. We
Oh,
already
sorry.
covered
I
the
didn't
moon
catch that.
filters. We covered the light pollution filters. There's a third category of filters called the
Pardon me.
planetary filters. These are colored filters, and you might see a set of them. If you are an absolutely critical planetary observer, then yes, planetary filters will help you.
Mm.
If you are anything less than like, this is my life, I want to observe every single detail possible from every single planet, planetary filters are not that useful. They do increase contrast. They do block out certain wavelengths of light that make it easier to use. But they're not, I don't think they're worth it. What eventually happens with the planetary filters, the colored filters, is you use them once or twice, you don't see a real benefit to them, and they end up in a sock drawer. There are other filters that are available for photographic use, but that's beyond the purview of this talk.
Right.
Those are useful.
Okay, any other questions? You didn't talk much about the go-to telescopes.
I did not. It's very complicated because there are different systems. It's basically like talking about computers. You've got your Mac, you have your PC, and you have, let's say there was some third type of computer beyond Mac and PC, and they all have different standards. There are 3 different standards in the go-to computer world. One is the Celestron standard. The other is the Meade standard. The other is what's called SynScan, S-Y-N-S-C-A-N, and that's for Skywatcher and Orion, and they all have different operating systems. So anything I tell you about Celestron is not applicable to Meade. Anything I tell you about Meade is not applicable to the Orion. And so rather than go into that level of detail and lose 2/3 of the audience here and 2/3 of the audience there, I think it's just best go to YouTube. I mean, I know I'm supposed to be explaining things, but this is something that, yes, while I can explain some things, it would just take far too long to go through everything. Go to YouTube, type in your particular handset, and learn from people doing presentations there. They're really good. If you don't like the way one guy is presenting it to you, skip to the next video, and you'll find somebody that will teach you in a way that you can understand.
Okay. Well, I guess, thank you very much, John. I think you have covered the area very well in detail. And so thank you very much. And
You're very welcome.
Also, thank you for all the attendees here. And
But I do want to say, and this is not a plug for the store, although it kind of is, but it isn't. What I've coined is that we're not Amazon. You can call us up at the store whenever we're open, obviously, or you could chat. There's a chat feature, and ask us whatever question you have. You don't have to buy something. It'd be nice if you bought something, but you don't have to buy something. We're there at the store. We're a resource, and just call us up, and we can answer your questions as well. And if you want to buy something, that's nice too.
okay.
Well, excellent presentation, John. Thank you very much.
Thank you.
You're very welcome. Thanks, everybody.
Yes, very well
Okay.
done.
So we can turn off the live streaming.
All right.